Hello, my name is Vanessa Angenent. I have already written my master thesis about combustion simulations for the Oxyflame project. In January 2018, I started my PhD and I am working as a research assistant at the Ruhr University Bochum on Project A7, the Atomistic multiscale simulation of char combustion.
Hi, I am Özlem Yönder. My first meeting with Oxyflame was back in 2016 as a master's student. At that time, I was working as a student assistant in Project A5. It was a lucky coincidence when I was later offered to work for A7. Like Vanessa, I have written my master thesis within Oxyflame. At the moment, I am finalizing my PhD studies and wishing to continue for this project as a postdoc.
Our Project A7 has started in funding period 2. We are working on the smallest scales in the Oxyflame Collaborative Research Center, namely the Atomistic scale. Our goal is to deliver theoretical data which is not accessible by experiments. We have two interconnected lines of research. One is building a char structural model and generating data for adsorption and diffusion. While diffusion determines the rate of combustion at high temperatures, at low temperatures the reaction kinetics are rate determining. Therefore, the other line of research is the kinetics, which Özlem will explain. Concerning the char structural models, to the best of our knowledge, there is no method in the literature to construct them with input parameters such as mass percentages of elements and porosity. I have developed a code that builds a char structural model starting from a random plane as input, which you can see in the background. In a proof of principle study, we have already compared adsorption values of different gases from our calculations with experiments from Project A6, finding the same trends for the gases. In the next funding period, I want to extend the model and generate a char structure construction tool which only requires minimal input, for example HRTEM images from A5 and chemical information like mass percentages of elements and porosity. That means we are able to generate models of all kinds of char by just pressing a button.
Complementing the work of Vanessa, I am performing highly accurate quantum chemical calculations on smaller systems. For this, I am using the partially in-house developed quantum chemistry package TurboMol. Like Vanessa has mentioned, the reaction kinetics are as important as diffusion. Therefore, to predict the reaction and activation energies of the elementary reaction steps, we have formulated approximate rules studying polyaromatics as char model systems. These rules are then transferable to kinetic models developed by other project groups. Additionally, in funding period 2, we have tested an already existing automated reaction network exploration tool, which had been shown successful for methane combustion. We have improved and extended its workflow to larger systems, and we have interfaced it with TurboMol. In funding period 3, we will be extending these studies to model systems including 5 and 7 member rings, oxygen-containing groups, sulfur and nitrogen heteroatoms, and inorganic phosphorus and alkali species. Another task is the computation of interatomic potentials. With accurate computed data, the quality of the interatomic potentials used to simulate adsorption and diffusion can be improved. Therefore, in funding period 2, I have calculated adsorption isotherms using coupled cluster theory. Thank you for watching this video. It was a pleasure for us to explain you our role within CRC.